Okay, so it's getting about that time, so let's go ahead and get started. So first things first, I'm Alec. A lot of you know me, some of you obviously don't. So we're here for CS1 today, CUP 3502. If that's not the class you're supposed to be here for, I want to double check the room number, go head out now. So on the board right now is kind of the table of contents and the outline for what I'm going to go over tonight. I might, if we finish early, I might do some like coding questions or stuff on there. Fair warning, I did leave out coding questions in this just because I feel like the coding can be a little bit subjective on some of them, and I feel like I don't want to mess with your guys' understanding if you already have a decent understanding. So most of it's conceptual stuff and stuff that only is like definitive, has answers, etc. Other than that, like I said, if I have time at the end, I have a few coding questions in mind I can go over. Other than that, I think I'm going to follow this. It's mostly weighted towards the new material, obviously, that you guys did towards the end of the semester. I'm going to briefly recap on some of the old stuff towards the end. I'm trying to go a little bit more in depth and more theoretical rather than just telling you guys, hey, do this pointer arithmetic or something like that. So I think we can go ahead and get started then. So the first thing on here is tries. So my first one is to insert some strings into the try and then into a try and draw it on the piece of paper and then answer a few questions about it. I'm going to give a little bit of forewarning. I did make this a little bit tight on space, so I'm probably going to skip a little bit at the top. So really quickly, just to start, all these I made the prefix comp on. So I'm going to draw a comp above this line up here, just so I have space to kind of put all the important nodes at the bottom. So really quickly, start with the root. Then go ahead and make our C, our O, our M, and then kind of drop that down to here, where I'll put the P. My apologies in the space. I was trying to not make my review 31 pages like Chris did. I don't want to kill that many trees personally, or write that much. So at this point, I kind of have to actually start doing each word one by one rather than starting going the way I am right now. So I'll do computer first. So computer, next letter is U, so I'm going to go far over to the right. Do my U, P. Wait, I just misspelled, oh my gosh. That's supposed to be an R. And if any point my handwriting starts to become an issue, please somebody flag me down. I'm well aware my handwriting is not the best. I'd say that's a reoccurring theme in the CS department. So next one I have compute. So if we follow compute down our try here, it'll go to the exact same node that's already been made. So I'm just going to increment the count in there and put a 1 there to indicate that that word has been stored in there. So now if I move to comp sci, so I already have the COMP. So if I want to do my S, I'm going to jump over a little bit to the right again. I will try my best to keep these as level as possible and kind of even across the paper. But these diagrams can be a little bit messy by hand. So there's our comp sci, and then jump to comp ng. Yeah, that looks about lined up. And then our last one is complicated. So put this one, probably should have, no, I shouldn't, okay. So if you guys ever have to draw a try on an exam, I don't think anybody will be nitpicky whether, if you put these orders right and get it alphabetized. These can get really messy if you're not kind of pre-prepared with knowing what the shape is going to look like. So I wouldn't be worried about having that expected of you. Okay. So now that we've kind of got the most boring part of that out of the way. Hopefully I didn't make any mistakes typing or writing it. Looks like it's fine. So my next question was, how many unique strings could be inserted into the try without using any additional memory? So if we're not using any additional memory, it means we can't make any new nodes in this try. We're going to assume that since I said unique strings, that we're not going to put in ones that are already in here, like compute, computer. So really what I'm asking is how many of these, how many nodes in this try other than the empty string or null string? So that would be this one up here. How many of these nodes are empty and could have a word inserted into them? So if we run through this really fast, I'll exclude the top one and I'll exclude all the ones that have a node and have a word already stored there. So then we have 3 here, 7, and then down the middle, we'll have 8, 9, 10, 11, 12, 13, 14, 15, 18, and then 22. So we have 22 of these, and then I'll subtract my ones. So 21, 20, and then 17. So at the end here, we'll have 17 words that could be inserted. Or I should say strings. I'm going to specify when I say the words strings rather than words. I'm going to tighten that up a little bit. Since obviously I could insert CO or CO, and while I don't think CO would be a word you'll find in the dictionary, it's certainly a valid string here. And then I said how many nodes are being reused in this try. So when I say reused, I'm saying how many words or how many of these nodes are being used by multiple words. Because when we look at tries and kind of the advantage of them, the advantage of a try is always that it saves memory, right? So if we want to know kind of an idea of how much memory it's saving, we have to look at how many nodes we're reusing rather than making new ones. So immediately off the bat, we know that all these ones at the top are being reused. So we'll have the 4 up here. Or I should say 5 down to this bottom one, including the P. And then other than those 5, the only ones we're reusing here are these 3 down here, right? Since they're being used by the word compute and the word computer. So we'll say an additional 3, and that'll come up to 8 down at the bottom. I'm going to have to slide this up a little bit. So then I said, suppose we call an insert string function on the node represented in the R in computer. So very end. What's the maximum length of a string that we can insert without increasing the height of the main try? Well, if we look at our try currently, our height is completely dominated by our word complicated. So if we check our height on that one, we'll have 5 nodes, 6, 7, 8, 9, 10, 11, 12. So our height would then be 11 at the top, 11 along the word complicated. So if we're inserting at this R, the height at this R is going to be defined by the word to get down to that path, or the path to get down to that word. So here we'll have our 5, and then our 9. We'll have 9 letters there. So that would mean our height there is 8. So which means we can insert up to 3 more letters after that from that R, using the R as like our root. So from here we could insert, I don't know, let's just say the word the or something. And then an E. And that should increase the height of the total try. The reason why I kind of threw this question here, even though it seems a little bit random, is that one of the things that you guys can always be asked is to use like a function on a try. And the key thing to remember about when you call functions on not just tries but trees in general is that you can pretty much all functions for trees and tries can be reused on other nodes other than the root, right? We don't always have to insert words from the root. We could insert at any point any node in that try, and it's not going to know the difference. None of the nodes in there necessarily know that they're not the root. So then moving on to this bottom section. Best and worst case runtimes for our insertion, access, and deletion. I wrote insertion twice, so let me just write deletion really fast. So when we're talking about our tries, our best case for insertion is always going to be the order of the length of the word. So I'm going to write it on the side here, where L is the length. All right, so if we insert a word into our try, scrolling back up really fast. If we insert the word super complicated or something, we're always going to have to propagate down all the way to the bottom of the try to be able to insert that word, because we have to create every node along the way and then update that count variable at the bottom, or whatever your specific application is. So no matter what, we always have to insert all the way down to the bottom. There's no case where that won't be the case. So in this case, we'll say our order is order L, or like I said, the L is the length of the word. And that will also be our worst case, right? Because no matter what, there will never be a case where we're going more nodes than the length. Now, when we look at our access, our best case time or runtime for our access isn't necessarily order L. Because if we are at the first node, even if there's thousands of words in this try, if we're at the root node, and let's say we're looking for the word phone, we immediately see from the root that there's no P. So even if there's millions of words in this try, if there's no P up here, then we immediately know that that word is not stored in our try. So in that case, we'll say that our best case access time is order 1. Now we talk our worst case access time. There should never be a case where we're going more than, if we're, let's say we're using for the word phone again. We'll never be going more nodes than the amount of nodes in that word, right? If we go down from the P, the H, the O, the N, the E, well, there's nowhere else we would go from there. We know we have our answer regardless of whether it's there or it's not. So in that case, we'll say that our worst case is order L. And then we look at deletion. So when we talk about deletion in our try, we always talk pretty much recursion, right? And even though we might be moving down and doing our steps in kind of a weird order, we're still only going to visit every node in the worst case one time in that word. So if we delete the word complicated, we will have to somehow propagate down all the way down to this D, but we won't have to branch off to the side and do anything with these other nodes. So every node in that line is visited once. So once again, we have our order L. And then for our best case deletion is going to be when it's not there, right? So once again, just like with access, if the first letter isn't in the top of the try, then we don't even have to bother looking through the rest of it. We can just stop right there. So once again, we'll hit that order 1. And when you think about this, this always makes sense, right? Because when we're accessing a variable in this try and when we're deleting it, it's still going to take the same steps to get there. We still have to somehow get to that bottom node that we want and then do whatever we're doing there, whether it's accessing it or deleting it. So it makes sense that those are always going to be the same. And then at the bottom, kind of leading into the next topic, I said, what is the advantages and the disadvantage of a try versus a hash table? To store it, and my example is to store the frequency of words in a given text file. So when we talk about tries, right, like we said here, is our worst case access time is always order L. And when we get that order L runtime is when the word is stored there, right? So if we're storing like all these words in a piece of paper, and like let's say a novel on a specific page, we're going to have to keep doing that insertion and that access over and over again. And that could be really bad for our runtime. So while our runtime isn't good there, we did talk about we were reusing eight of our nodes in this try. So memory-wise, we're saving memory, right? Our space complexity is better than if we had a hash table where we're storing every single node. Because when we talk about hash tables, we know that every variable will be stored in a hash table. We don't get to reuse any of that same memory. We don't get to do any of that kind of reuse that we do in the try. So I will put try hash table. And then under our hash table, we know our runtimes of our hash tables are very good, the best pretty much we'll ever see in data structures in this class. So we will know that the hash table has better runtimes. Put plus next to that. But like I said, it wastes memory. There's memory that's going to be, we can't really reuse memory in the same way. So even though I might be storing the word computer and compute in the same hash table, they're going to have their own section of the hash table, so we can't really reuse the same way. So then I'll say the minus is storage. And then, like a lot of these comparing disadvantages and advantages, the advantages of the try are just going to be the opposites. So runtimes, and then I'll move my hand out of the way. So in general, we want to use tries when we're worried about running out of memory. And while that seems something really silly to worry about in this class, and something that he has never told you guys to worry about, there's a lot of applications that does still matter. Even though we think about like our computers, oh, like we have gigabytes of RAM, who cares, right? I've done programs with tries before where I've stored all the words in the dictionary before, and it'll easily start consuming like half a gig of your RAM before you can really have much time to worry about it. And that was in a try, so if you do a hash table, it's going to get monumentally worse because we won't have any of that reuse we're talking about. And same thing with runtimes, right? So you just kind of have to evaluate whether you're more worried about your runtimes or your storage. I'll kind of give everybody one last minute to finish writing down if they need to. Am I good to go on? Yeah. Nobody still writing? Crap, where'd that stack go? Okay, so the next section on our thing was heaps. So this one's pretty straightforward. I think this is a pretty fair exam question because we know that heaps is going to definitely be on there somewhere. Oops. It's a little bit crooked, but whatever. So all I said was to do all the insertions for this heap and then show you kind of the steps each way so that you can tell what the heap looks like after each insertion. So first thing I'm going to do really quickly for my own sanity is I'm going to number these so that I know which step I'm on. So starting at the beginning, we have to insert 19. Hopefully we all know how to insert 19 into an empty min heap. I'll just put a 1 next to it. So we'll just have our node 19. Obviously there's no steps there, so don't really go too in depth with it. So with our second one, we know that in heaps, we always worry about our structure before we do our percolations. So if it's a complete tree, which it always should be in a heap, we're going to insert to its left child. So we'll insert our 7 here, and then we'll deal with that whole situation of who needs to go where. So when we look at this, we'll go from our 19, and we'll say, okay, is our 7 smaller than our 19? Because if so, it needs to be at the top since it's a min heap. Obviously, in that case, this is true, so we'll do a swap. And we'll end up with 7 and 19, and that's our second one. So moving on to our next part. Once again, we're going to worry about the structure before we worry about the order. So we'll insert 12 to the right in the right child position, and then we'll do our evaluation. So if we look at compare 12 to 7, obviously 7 is less than 12, so we'll leave it there, and we'll say that one is good. Let's see, and then moving on to our next one. I think after this is when it starts percolating. So 7. Insert it in the left child of our 19, so we want it in the leftmost position of the next row. So at this point, we've increased our height. So it was 20. So when we insert our 20, once again, we don't have any movement, so we're just going to leave it as is and call it good. Seven, 19, 12. Then insert the 4 next to our 20 since we're going, once again, filling in the bottom row from left to right. Let me just separate that a little bit. So when we put in the 4, we'll put it in, we'll make sure our structure is still right, because we always want to maintain our structural property of our heaps. And then we'll do our evaluation, so 4 and 19. 4 is lower than 19, so we're going to do a percolation up. So then we'll have 7, 4, 12, 20, and then 19. We'll check our 4 with our 7 now. The 4 is once again smaller. So we'll have to do one more percolation up. And it's important to remember when we're talking about heaps that while this is a complete binary tree, it's not a complete binary search tree. This isn't can't say that things to the left of an item are smaller or bigger. We have no idea. All we can ever say is that the top value, every parent is smaller in this case than its children. So we'll put our 5 there. So moving on to our next one. I should move that over. So we've inserted our 1. Now looking at our values and which way we need to move it, we can tell that our 1 is going to have to move up. So we'll do the first percolation. 4, 1, 12. And then we compare our 1 to our 4, and our 1 is going to be smaller, so we'll move that up. And the one thing I'm going to say is that while this is obviously looking extremely straightforward, if you try to skip a step, it will backfire almost every time. These percolations can get a little bit weird sometimes, and you just got to be careful that you don't mess up a step along the way. And then that was 6. So at this point, we're inserting our 14. So we'll do our checks. Everything from the 4 is smaller than our 14, so we are good. We will leave that there. And then next we're doing our 3. So we filled up our heap currently, so we'll have to add in another row. So we will go to the farthest left position in our next row. So now we will do our percolations. We can obviously see that that's going to have to move up at least once or twice. Oops. And that's where I would have just made my mistake. And while I'm urging to make sure you do your steps in heaps, this applies doubly so to AVL trees. If you do an AVL tree and you try to skip a step and just kind of get ahead of yourself, you will almost 90% of the time mess it up along the way. I really would urge you to do every single step and kind of show your work, especially if you want TAs to give you partial credit. And that was our 8, so we're almost done. So we got to insert our 24 now. So insert it next to our 20, and we will see that that is fine. We don't have to do any percolations here. And we'll move on to our last one. So in our last one, we're doing our 6. So 3, 4. Sorry, these are getting a little bit close together. So when we do our percolations, we know the 6 is going to have to move up. All right, 6 is less than 19. So 1, and then our 3, 4. And our 14. So at this point, we'll look at it. Everything looks good. So we have finished inserting all of our elements. And I didn't really write these questions on here, but I'm going to ask to just do a couple more things really fast with it. So when we're looking at our heap, we always talk about, we've talked about Heapify a few times, right? And I know that Dr. S has mentioned to make sure you guys are all familiar with that, for all of you that are in his class. And then even if you're not, and if that's something you guys haven't talked about, it's going to be in the foundation exam. And most of you are probably taking the foundation exam. So very briefly, we're talking about Heapify. We know that Heapify is kind of just going back and forth between an array and a heap. Since if we use an array for a heap, we'll get our better run times. So really quickly, I'm just going to write down if we did the array version of this. So if we did the array, we'll go across each row left to right and fill in our array. Like that. Oh, got him, right over him. I'm going to have to write this down here. So this would be if we stored our heap in an array. This would be what the indexing would look like. The formulas you can use to kind of go back and forth between these has been shown before, so I won't really expand on that too much. If we want to talk about the height of this heap, we know that if the height was starting at the top, we'd have 0, since an empty tree has a height of -1. So if we're currently 4 tall, we're going to say our height is 3. Sorry if I'm like standing kind of in the way of this left part. Oh, actually I can slide that over quite a bit. Okay, cool. So now we've stored everything in our heap. We've showed you every step, so we're good to move on to our next question. Anybody still writing? Okay. So our next page is a little bit more heap stuff, a little bit more interaction rather than just drawing it. How far can I go over? Okay, hold on, let me straighten this out. Just a little. There we go. So our first part says, what are the guaranteed characteristics of a min/max heap? So we have 2 properties we're always guaranteed to have. Of course. Okay, cool. So we have our 2 properties of heaps that we're always going to be concerned about. We have our structural property and then our ordering. I think there might be another term for that, but we don't really care about the name. So with our structural, just like we said on the other page, we said that it was always a complete binary tree, but not a complete binary search tree. So we know that it's a complete binary tree. And then our other property is that we're guaranteed, I'm going to say for a min heap in this case, since that's what we just did, that the parent is always smaller than its children. And while heaps seem kind of basic and kind of unneeded compared to some of the other structures you guys have dealt with this semester, there's a lot of applications in heaps when you guys go on to CS2 if you're going to be taking that, and just later programming later on. So these kind of 2 characteristics can kind of lead to a lot of good things, and some of it we'll talk about a little bit later here. So then I just said, what's our best and worst case runtimes for insertion and then deletion in our heaps? And then what causes our runtime to go from like bad to good? So I'm going to kind of split this really quickly. So we'll put best and then worst. So hold on, let me just grab the other sheet so I can kind of talk to it. Yeah. So we're talking about our best case runtimes. Actually, I can use the one at the bottom here. We'll just do that. So our best case, if we're doing our insertion, if we insert a node and it just kind of fits where it is, right? So if I insert something here, and this is just exactly a location where it can go, then at that point we've hit our best case runtime. So we just insert it, and we don't have to do anything with it. We don't have to do any swaps or percolations. So in that case, we'll say it's order 1. So for deletion, when we delete from a heap, let's see, I'll do it in the back of this. So really quickly, I'll draw a little small one. So if I delete out of this min heap that I've just thrown together, we know that we can only ever interact, delete, look, peek at our first value up here, this 1. So if we're deleting our 1, we'll immediately remove that, and then just like before, we'll maintain our structural property before we maintain our ordering. So in order to fill this gap, we know that our one that's going to disappear is going to be the one down here, so that it remains as a complete binary tree. So we'll delete, or not delete, but we'll move the 7 up to the top, and we'll put our 7 there. So at this point, our 7 has to do a swap down. Now, when we do this, we're always going to look to the left before we try to do anything to the right. So in this case, our best case runtime would have been if we only had to do one swap here, right? Because it's guaranteed that if our tree is however large, that this 7 has to be bigger than what's over here. If we're assuming it's very large. We have to say that it is guaranteed to at least do one movement. It'll never just go up to the top unless this heap is just one level or 2 levels high. So our best case is usually going to be when this side of the heap that we're kind of pulling out of is going to be all smaller than this right side. So if this was, for example, let me put in some very large numbers, like 100, 110, and 120. Then at this point, we might only have to do like up to one swap or less. So it's kind of when you have one side of your heap that's going to be significantly different than the other side. We can do really fast run times. So let me do one better example. So if we have, let's say, 2. So that was a 1 at the top before, so yeah, that's fine. So we'll say 2 and then 192 and 100. So at that point. So this is one where we'd hit our best case runtime. If we pulled that 7 up instead of that 1, we obviously see it'll swap with the 2, and then it'll stay there because the stuff below it is so much larger. So that would be one of our best case runtimes for our deletion. So in this case, we're doing one swap, which in the longevity of things, since we can do that for an infinitely large amount of nodes, we'll still say that for all intents and purposes, that is order 1. So now for our worst case. So when we talk about insertion, going back to this one, our worst case for insertion, right, is going to be if we insert in a min heap, is going to be if we insert something that is so much smaller or larger, depending on the min or max, that it has to move up to the top. We have to percolate all the way up to the very top of our heap. Since in this case, let's say down here, if we insert something, we worst case, we're going to have to do 3 percolations, right? So this isn't necessarily like order n or something really bad. We're going to say that this is always going to be order log n for our insertion. And the reason we say that is because our log n is going to be our number of percolations to get up to the top. So we know we can find the height of our binary trees or any type of tree really by doing the log to find the log of how many nodes are in it, and then taking the floor of that. But regardless, we say that it's log n to kind of percolate up from the bottom all the way up to the top. So in that same kind of vein, we'll say that for deletion, our worst case is going to be, okay, let's say we delete our 12, and our 33 moves up, and it has to percolate all the way down to the very, very bottom, which in this case, it would not, but we can pretend it did. So if we have to percolate all the way from the top to the bottom, we're once again doing logarithmic amount of percolations to get it all the way from the top to the bottom. So it'll also be our order log n. And then I asked what values can we store in this insert into this min heap that would cause our best case and worst case runtimes. So we said for our best case for insertion that it's when we insert an item into there and it already fits. So if we look at this min heap, we know that the next location we're going to store something in is going to be right here. So we want to store a value in there that's going to kind of go into that location and then just never have to percolate. So in this case, we can insert any value that's greater than 24. So I'm just going to write here. So I could insert 25 in there and it wouldn't have to percolate up because this comparison would always hold true. Actually, I should say this should be, let me write this really fast. I should say or equal to, because we could also insert 24 in here, right? 24 wouldn't cause a percolation. So if we're talking about our worst case, we already said that our worst case is when we have to percolate all the way up to the top. So if we have to percolate all the way up to the top, we know that that's going to have to mean that our value that we're inserting has to be the minimum, because it's moving all the way up to our minimum value at the top. So in this case, it just has to be something that's with this 12. So let me write the 12 in. So this value has to be, we're going to say, okay, are we going to say less than or greater, or less than or greater? Less than or equal to, like we did before, or should we say just less than? Somebody? Shout it out. Somebody? Yeah. So if we say less than, if we say equal to, let's say we insert a 12 right here. So this 12 is going to percolate, swap with this 24, and it's going to swap with this 23. just going to look at the top and it's going to say, okay, should I swap with this 12? And it's just a waste of our time if we do a swap between a 12 and a 12. So it will never do that evaluation. So we want something that's less than and not equal to. So going back up to right here, I said what caused, or I said in this part actually, what caused our best and worst case runtimes? Like what causes us to kind of move along that spectrum from order 1 to log n, because that's obviously a big difference. So in this case, it's the percolations, right? When we're doing no percolations, we were saying that was our best case runtime, and we were doing all the possible percolations. That was our worst case runtime. So this kind of the answer to that is just number of, oh god, how do you spell percolations? I'm totally guessing on the spelling of that. Don't judge me. Okay, so then at the very bottom, this is kind of one of my first kind of theoretical type questions. So I said, what sorting algorithm functions similar to heap sort, and then which one's better and why? So when we talk about heap sort, right, when we do our heap sort, we just insert all of our values into our heap, so something like this, and then we just kind of pop them out over and over again. Since we're guaranteed that every time we delete a value from this heap, it's going to be our minimum value. So in this case, if we kept on deleting, we would delete our 12 and then our 17 and our 18, and that we're always guaranteed that that value at the top is going to be our minimum value, unless we're doing a max heap, obviously. So every time we kind of do our operation, we're always pulling out that minimum value. And I don't know if that's sounding familiar to anybody yet, but this is going to be kind of similar to our selection sort. So selection sort, like if we remember, always just goes through our array and just kind of finds either the minimum or the maximum value, depending on how it's coded up. And it just kind of grabs that value and swaps it up to the front. So just kind of like that, just kind of like in selection sort, heap sort will always give you that minimum value over and over again. But when we look at our runtimes for selection sort and our heap sort, really quick, I'm just going to write this at the bottom. So heap selection. So when we do our heap sort, we say it's always going to be, and this is just, we're going to do best up here, and then I'll do worst. Our heap sort is always n log n. And that's because we have to insert n elements, and if we're inserting n elements and then deleting n elements, then we might hit our worst times unless it's already sorted. Because no matter what, we are always doing like these kind of slow operations, regardless of whether what the order is. And that kind of stems from this whole overhead cost we have with our heap sort, right? We have to build that heap in the beginning. So then. Slide that a little bit that way. So when we talk about our selection sort, hopefully we can think way back to then, is that our best case was order n for when everything's already sorted and it finds all its values as soon as it can possibly. But our worst case for selection was an n squared, right? It was an n squared sort. It was kind of during that bad time, and we don't want to, the sorts we never want to use, because if we're doing a selection sort, we might have to go through here n times to be able to find every value. And if we have to go through every value in it n times, then we're going to hit our max very quickly, our worst case runtime very quickly. Well, with heap sort, we're always going to have our n log n. Because no matter what, these percolations will always work out to our n log n. It can't really get any worse than that. So when we compare these, right, there's kind of a mix here. Because order n could be better than our order n log n. Our selection sort can beat our heap sort. And you'll see if you do want to do the calculations, which I have a feeling most of you probably wouldn't want to because it's not very entertaining. But if you do the calculations, it's something up to like 50 or 100 elements or so. Our selection sort will beat our heap sort. But at some point, just the randomness of our ordering of our selection sort will just kind of win out. So we talk about which one is better. So while usually we kind of just look at our best case here, this worst case is significantly worse than n log n. So we kind of would rather always do our unstable here, because we always want to assume that we're doing a large amount of elements and then we're not doing 10 elements. In reality, when we look at sorts in the real world, usually we'll end up doing multiple sorts depending on the number of elements. But for now, we're just going to assume for our largest amount, we want to use our heap sort. So for why is it better? Like I just said, we're going to want the one that's going to always run in our n log n time rather than worrying about hitting that n squared runtime, which for a lot of elements could be a significant amount of time. or I should say reliable. How about that? And it makes sense, right? Because we're kind of, when we do our heap sort, we're kind of investing that initial time into inserting all of our elements. So unlike our selection sort, we're kind of going through repeatedly over and over again and repeating that same process. We're always, in our heap sort, we're kind of doing that initial investment, and then we just have to worry about the percolations that might occur afterwards. Is anybody still writing? Okay. So moving out of our heaps and into our hash tables. What am I doing on time? Let's see. Actually, let's start it. So I said at the beginning, use the following. I gave you as a hash function. I'm not too worried about whether we can do this math, but I gave you as a hash function. I said, okay, insert all these elements using linear probing, quadratic probing, and then separate chaining. So let's think. What's going to be the best way to go about this without wasting a bunch of time using this doing the calculator? So really quickly, I'll do a couple of these in front of everybody, and then I'll just kind of tell everybody what the values are coming out to so we don't continue doing this. So let's see. I'm just going to throw this right here. Let's see, is that screen going to be readable? Probably not. I might have to say what it is. So if we do our 56, and we plug it into our function up here, so we know in this one our size is going to be 12 since we have 0 to 11. And then we know that our key in this case is 56. So we're inserting our function, we're plugging in 56 and then 12. So we'll do 56 minus 20 times 5, and then modulus by our 12. So in this case, this is 36 times 5 mod 12. So 36 times 5, I do not remember that off the top of my head. Actually, yeah, it's 180. So that'll be 180 mod 12. So there's two ways you can kind of calculate this if you have to on a test. You can either look for kind of powers of multiples of 12. So in this case, we know that 120 is obviously a multiple of 12, right? So we know that we'd be subtracting that out of our value. So if I was doing this, I would probably just subtract out that, and it's going to be 60. Then we can say this is going to also be equal to 60 mod 12. 60 mod 12, if we know that 60 is a multiple of 12 since 12 times 5 is 60. So then we'll say that this is equal to our 0. So we're going to insert this at position 0. So we'll go in here and we'll put 56 at position 0. And then I'll kind of try to speed this up a little bit. So when we do 41, I'll do like 1 or 2 more, I think. 41 minus 20. So that's going to be 21 times 5. And that's 105. So 105 mod 12. Once again, I don't remember this number off the top of my head, so what I always do is I'll just start subtracting multiples of 12. If you want, you could also just keep subtracting 12 until you get something less than 12 if you're allowed to use a calculator, depending on your professor. But let's assume we're not, so we'll say, I know 90 is or not 90, we'll just do 60, so if I subtract 60, we'll get 45 mod 12, and then I'll subtract 36 from that. So if I subtract 36, that'll be 9 mod 12, which is equal to 9. So we know we'll have to insert 41 at our 9th position, and then from here I'll just kind of give us the values. So that's 0, 9, this was 9, 10, 1, 8. For all of you in Dr. S's class, I don't think or last time I checked, unless he's changed his mind in the last few days, he's not going to let you guys use a calculator. So in that case, if he gave you this, he'd give you like a really easy hash function that was coming out to a nice, clean value. He wouldn't make you guys do this kind of math unless it was like 3 values or something. So if I go to insert all these, so as I've very unneatly written over here, 65 also hashes to our ninth position. So we're going to have immediately have a collision, so we're going to have to actually use our probing method now. So in this case, we said use linear probing, so okay, we'll just throw our 65 then in 10. Moving on to our next one, we do 22. 22 said it was supposed to be inserted at 10. So once again, we have a collision, so we'll insert 22 here. I'm just going to mark this as a collision, this is a collision. And then our 37 is supposed to go in 1, and our 48 is supposed to go in 8. So with linear probing, we had our 2 collisions there. But as we can see, this is really clumped up, which is, as we've talked about in class, or you guys have heard in class, is that when we have clumped up hash tables, it's usually a bad sign. It's that either our variables are following a specific pattern, or that our hash function is bad, which in this case it probably is that. So on to quadratic probing. So quadratic probing, we're using the same hash function, so we're going to find these values the same way. The only thing that's going to change is that the size variable is going to change, right? We have 13 positions here for reasons that we'll discuss later. Hopefully you guys already see why. But the size here is 13, so the mod would change a little bit, but I don't really think I need to rework a bunch of those. So if I give us the positions, this is 9, 3, 4, 12, and 0. God, that made that so much worse. So start at our 9, inserting our 40 there, insert 57 at 3, and then we're going to insert our 91. So now we're going to have to do 30. We're going to have to insert 31. So if we insert 31, it said it hashes to 3. So if we try to insert 31, we obviously have a collision there. So we have to use our quadratic probing. So we do the position we want to start in. So we're going to call this guy I. And then for every time we have a collision, we'll say I plus, or actually let me call this position like n. It's probably better. We'll say I is the number of times we collide. So we'll say n plus I squared, where I is the number of collisions. So one thing with quadratic probing, and the easy mistake here to make, is so we know that we're going to immediately try to move it 1 position, because we'll do our n position, which is 3, plus I squared, which we have 1 collision so far. So we're going to do 3 plus 1 is 4. We'll try to insert it at 4. That's going to cause another collision, so we'll do n plus I squared. So that's our n plus 2 squared, which is 4. So the big thing to remember here is that we're not going 4 positions from here. This is probably the number 1 mistake you guys will see with hash tables, is that people are going to try to do 4 positions from here. If you're going to remember it like a formula like this, always make sure you start from your base position. I'd recommend just doing the math quick, and this should also technically be mod the size, but that's not going to matter in this case. So it's really easy to kind of make that mistake and then go 1 item too far, and that causes your entire thing to be screwed up, and that will cause more collisions, which then everything kind of piles on top of itself until your entire problem is wrong. So in this case, if we're going 4 positions from where we started, 3 plus 4 is 7, so we're going to insert our, 31, right there. So we had kind of like 2 collisions here. So inserting our other 2, they look like they're going to come out fine, so we'll insert 25, and then we're going to insert our 20. So like I said, this is probably the easiest place to make the mistake, is right here, is when you're doing those inserts and you're not keeping track of, you're not going from the initial position, you're going from your current position. If you want to try to do that from that current position, you're going to have to do some subtraction and other math, and you're probably more likely to make mistakes. So moving on to our separate chaining. So I'll give us the values. I put a few more in this one. So our first one is 21, and we're inserting it at 5. So I'm gonna start doing this by hand, and then I'm gonna show you a shortcut if you ever have to write this on paper. But for now, we know that we're gonna in each of these locations we're gonna be storing an address, right? So this is gonna be like 0x like 1, 2, 3, 4 or something like that. Some hex number that represents an address that none of you guys care about. So it's gonna point to a linked list, which would start null originally, but we'll malloc that node, make our start of our linked list, and we'd insert 21 there. So if we keep doing that for our other ones, 41 would go right there. And then R25. I promise this gets less boring in a second. So it's 27. God, why are the collisions so late in this problem? 38. So for each one of these, it's important that we remember that each one of these is going to be a separate linked list, since we're doing separate chaining, as the name implies. And that our insertion time here is still going to be our order 1, right? Since the only difference is that instead of inserting just immediately into that array position, we're malloc-ing that node in the linked list and throwing it there. So that was the 44, so then our next one is 36, finally. Okay, so when we insert our node for our 36, so our 36 is going to go at 8. Now, should we put it below or above the 27? Above? Anybody saying below? Okay, yeah. So it should go above, and that's because if we want to put it below, right? Let's say that this is like 30 items long coming out. We have to go all the way down through that linked list to the bottom to put it there. So instead of trying to do a tail insert and all that stuff, happy linked list stuff, we're just going to insert it at basically at the head of our list here. So in this case, we're inserting our, that was 36. And then the other one was our 27. So the kind of little trick to these is if you ever have to actually write this out on a test, is do it backwards. Because if you do it backwards, if you go from back to front, you know that this last value goes at 6, you know that's going to be the first thing in this list. So I'm going to erase all these ones that have collisions. So that's 5, 6. I think that's the only ones we have to change. So if I did these from the back, so from the back, we have 3 items. We have 32 goes at 6, we have 23, and we have our 41. And then on the 5, we have 30, and we have 21. And that's all of our values. We can double check really fast, because we have 5, 8, 11 nodes, and then we have, 11. So we've inserted all our values, so this would be what our separate chaining would look like. So it's important to remember that these boxes never hold the actual values when we're doing a separate chaining. They'll always hold a pointer to an address that will go to our linked list.
So the reason why we insert the head is because more recent data is more likely to be accessed? Is that the only reason?
So not necessarily, but it's more to do with our runtime to get down there, right? So if you think about a linked list, if we want to insert at the tail of a linked list and we don't have a tail pointer, then we have to do, it's going to be an order n time, where n is the length of our linked list here. So if this was like this many values, let's just keep saying I go down here. So if I had all these nodes here, then I want to insert another thing at 6, and I do it at the back, I have to go through all 6 of these nodes to kind of get down there. And if that gets really big, then we have a lot. It'll take us a lot of time. If we just insert at the front, then we can kind of just destroy this link up here, put our new node in, and then reconnect it. And it allows us to get our order 1 insert time that hash tables are known for in this case. So it's a little bit more about our insertion time rather than it is about accessing our data. And while that is probably true that our more recent data is probably more likely to be stored, that's not something we worry about we're worrying about here. Because we're only ever looking at best and worst case runtimes, right? We don't ever look at average case in this class. So when we're looking at our best or worst is still going to be when we're accessing it, having to go to the end of that giant list. And our best case will always be as if it's in that first value in the whole chain there. So my next question on here was, what are the requirements to be able to use our quadratic probing? Because unlike the other two, quadratic probing is kind of a little bit special in the fact that we can get infinite loops.
It has to be double the size and then to the next prime number.
Yep. So it always has to be, I'm going to say less than half full. And then the size always has to be a prime number. And I think it has to be a prime greater than 2, which hopefully your hash table is never of size 2. So the reasons for this is like I said earlier, is that you can cause an infinite loop with quadratic probing, where you're just always going to the same nodes over and over again, and it also makes your runtime really bad if you're having to go through like 6 or 8 quadratic probes. I don't know if that's the correct term for that, but kind of 6 or 8 positions enabled before you can find your position. So we want to do that so that we're always guaranteed to find a spot. So don't stress about like whether this is less than or equal to, because if we're doing a prime number and it has to be greater than 2, every prime number greater than 2 is odd, right? Otherwise they're divisible by 2. So it obviously can't be less than or equal to, because it's never going to be half full if it's a prime number, or if it's an odd number. So it doesn't, for all intents and purposes, it doesn't matter if it's less than or equal to. We don't care. And we're talking about separate chaining and linear probing. While it's not required for those two that we do our half full, in general practice, we will always keep them less than or equal to half full. Because if we start letting them get, like our linear probing get really full, then we might have to go through every position in this, right? It helps keep our runtimes on the lower side of that and possible runtime for that in that case. So then down here I said, what are the advantages and disadvantages of using separate chaining? So the advantage is the more obvious one here. So our advantage is that we get that order one insertion time, right? Because on worst case insertion time, I should say. So in linear probing up here, our worst case insertion time can be order n, because we might insert it 1 or 0, and it might have to go through every single position before it finds an opening at the very end. And same thing for quadratic probing, but it's a little bit more complicated of watching it jump around. But it might have to go through every single position to find a position that it can use. So those two both have an order n insertion time. When we look at separate chaining, like we said earlier with using the linked list and inserting at the head here, is that we always ensure that order 1 insertion time. So advantage. And then we don't change our insertion time or our access time, because we're still going to say it's order n for accessing all 3 of these methods, because just like I said before, for linear and quadratic, we might have to go through every single element down that line. But just like the other two, our separate chaining, the worst case is if everything collides at the same position. And in general, we can say for hash tables, our worst case is almost always when everything collides at the same position. So if everything hashed to the same value 6 here and every other space was full, if we wanted to access a value in here, the worst case is if we go through that entire chain all the way down, going through our n values until we find our value at the very end. So our access time will never change. So our disadvantage of our separate chaining, does anybody have any idea of what this might be? Go for it.
50% of the things that you evaluate is in one hash bucket.
Yeah. So
Everything goes to one bucket out of like 10.
yeah. So it's kind of the cause, and we'll talk about the effect here in a second too. So with all these, like I said, the worst case is almost always that we insert everything to the same position. So in these two cases, it'll cause our entire entire hash table to become relatively full. The other problem with when we do this linked list, though, right, is that let's think about the storage we're doing here, right? So when we do these two up here, this is probably let's say it's an array. This is an array of like our 11 numbers, right? But down here we have an array of 11 pointers, and then we have every node that's associated with those. So this is going to immediately start taking up more memory, probably somewhere around double or so, depending on how full you make it. Because all these pointers are going to be taking up, for all intents and purposes, the same amount of memory as that these integers will be taking up. But these ones up here don't have all these nodes that are having overhead afterwards. So these will probably about double, maybe even a little bit more than that, the amount of memory that you're going to be using for each of these values. So memory-wise, it's worse. So like I said, while you guys might not be too worried about your memory in the class, depending on what you end up doing in life and what job you end up doing, there is still, believe it or not, there is still technology out there that relies on small amounts of memory, like embedded systems and etc. And if you guys take comp org, you'll probably talk about it in there. So, am I still writing? We're good to move on? Okay. Actually, really quickly before I move on, actually. Which one of these was I using? I was using this one. Really quickly before I move on. So, when we look at our hash function up here, does anybody remember what the kind of key factors that decides whether a hash function is good or bad?
Its range of values.
Yep. So, yeah, we want to make sure we can get at least all of our values. So it has to, this maximum range of this has to be able to get larger than whatever we're modding it by. So if we're modding it, if we have this giant hash table of like 1 billion values, we have to make sure our hash function can make numbers larger than 1 billion, which in this case obviously might not be true. Multiplying by 20 or subtracting by 20 then multiplying by 5, we probably will never reach those. So if we use this hash function, it'd be really bad, right? If this was like size 1 billion, we'd be getting values that were like all under like a couple hundred. We probably wouldn't be getting very large into our size, and we'd be having a ton of collisions. And when we're talking about our hash tables, there's two things that always make our runtime bad, right? It's when we have collisions and we have to do our order 1 access time becomes order n, and then when we have to enlarge our hash table. So if I make this hash table and we start filling this, and I want it to be less than half full, we have to enlarge it when it hits that half full mark, right? But like we talked about in class, when we make a hash table bigger, if I make this 24 slots wide, or 23 I guess, 29 I think would be the value we go to, we can't just leave all these values here, right? Because if we leave them all here, and I say, okay, let's plug 57 into this function up here, or 51, or no, it's 57. This isn't going to be the same value anymore, because we're going to be modding it by 29 now or something. So it's going to hash to a different value, and we're not going to know where it is anymore. So we always have to rehash and reinsert every variable in here. And while that seems really, really, really bad, right? Like, we have to do all this work if we're storing let's say we're storing 1 billion values in there. We're going to have to rehash 1 billion values, and that's going to be really bad. But when we think about it, to get to 1 billion or 2 billion, let's say we start with a hash table of like size 8. It's like 20 duplications, or 26 or so duplications to get to that size of billions. And when we're talking about this storage that might be taking up billions and billions of elements, we don't really care that we're duplicating it like 20 times, right? That's a lot less than billions. So we usually don't really care that we have to redo that value just because of how fast it grows. So back to talking about what makes our functions good. So we have to have a good range of values. What else do we need? Yep, we need an even distribution. So if we use this hash function, once again, we'd get all sorts of overlaps. It would be really bad. And that would cause a lot of collisions, which once again makes our runtime become very poor. We want it to evenly distribute things as much as possible while still being deterministic, which is the last thing. So I'll just write this kind of at the top up here. So full range, even distribution, deterministic. And I want to say I want to make sure I always mention it having to be deterministic, which if everybody forgets what the word means. It just means that every value will always hash to the same thing. And while that seems really like, of course, why wouldn't it ever hash to the same thing? If we're wanting some really large, like random value that's be like, let's say billions long or something to build a mod by our size here, the easiest thing when I say random value of size billions or something is to use like a random function, which would then break our it being deterministic and would cause all sorts of issues. So it's important to find something that's random while still being deterministic, which is a whole other problem on its own that you guys may or may not face later on. So moving on. Oh boy, base conversion and binary. I'm sure we're all really excited for this one. So some of these are really straightforward and are pretty easy. Some of these I purposely put in here to show you that there's tricks to these and that they're not always as nasty as they seem. So if we're doing 277 to binary, I'm going to do it the method that Dr. Zemansky uses and a lot of the other professors like to use, and that's the division by 2. So if I divide this by 2, I'm going to get 138 with a remainder of 1. I'm just going to write 1. And then I'll keep dividing that by 2 over and over. So 69 and 0, 34 and 1, 17 and 0, 8 and 1, 2 and 0. And then 1 and 0, and then if we divide 1 by 0, oops, sorry, that should be remainder of 1. If we divide 1 by 1, hopefully we get, or 1 by 2, we should hopefully get a remainder of 1. So now that this is perfectly not quite even, we string all these numbers, our remainders together, and we put them in a reverse order. So we'll have this 1, 0, 0, 1, 0, 1, 0, 1. Double check that I wrote that right. Looks like I did. And there's our value. Relatively quickly, I feel like this value is pretty fair to ask you guys to do in your head or on paper. The other method being determining what your biggest factor of 2 is in there. So you could also do it as like 277 minus 256, and then you know that that first spot is 0, and then that's like 21, and continuing on from there. So then at that point, you could do that kind of subtraction down each step of this ladder to figure out if it works. So if we want to do this one, we can kind of do that same methodology, where we're going to divide our 543 by 7. And that is, since I do not expect you guys to remember that off the top of your head, 77 with remainder of 4. And then we'll keep doing that division over. So 77 divided by 7 is 11 with a remainder of 0. And then if we do 11, we get 1 with a remainder of 4. And then if we divide 1 by 7, we'll get a remainder of 1. So now we'll do the same thing. We'll string these up backwards, and we'll have 1, 4, 0, 4, base 7. Relatively fast, right? Not too painful. And then it gets painful. So there's 2 ways to do this problem. And I'm going to say that one of them is right and one of them is wrong. And I'm going to say that because this is really awful if you do it the long way. Especially if I can totally see one of the professors giving you guys a really long one and expecting, if you don't know the trick, you won't be able to do it in time. So the first way you can do this, it's probably the most obvious, is just to convert it to decimal and then convert it to hexadecimal, or to hexadecimal, which will be really long. I don't really know how many digits are there, but it's enough that you're probably in the millions. So I personally don't want to do it that way. So what I'm going to do is, since I know that this is the power 2 and this is the power 16, since this, if we have our 2 to the 4th equals 16, right? That means that for every 4 bits in this, it comes out to 1 hexadecimal digit. And we can do that for any 2 bases that are a power of each other. So let me write that up here so I have space. So since I said that there's 4 bits in every hexadecimal digit, I'll immediately break this down into chunks of 4. And I apologize, this might be a little bit hard to read. I'm going to try to just put little dividers in there. And I think if I remember correctly, the last one has 3 digits, which it does. So since this last one has 3 digits, I'll just throw a 0 in there just to be kind of clear, and then throw a break. So now, if I work from the right, so in this one, obviously we have a 1, a 2, a 4, and an 8. I'm trying to write those as small as possible. So in this one, we have 4 plus 2 plus 1, which is 7, and 7. I'm just going to write the 7 in kind of like decimal for that set. Our next one, we're going to have just a 4. I'll put some like little arrows here. Our next one, we have 8, 4, and 2, so that's going to be 14. We'll check, yeah. Our next one is the same thing, so it'll also be 14. Our last one is 8 and 2, so then that'll be 10. Sure, the 10, through the arrow. And then our last one is just 8. It's like, okay, so that's obviously not in hexadecimal. But all of these will have a maximum of 15, right? If I had all 1s in one of these, so that's just this one but with a 1 at the end, the maximum value is 15, which coincidentally, not really, is the same range that hexadecimal values do. So if you convert these into hex from these decimal values here, we'll have 7, 4. So in hex, we know that 15 is the highest value you can get, and the highest value in hex is F. So if this is 1 less than F, then this is E. and that's E, and this is A, and this is 8. So that's our final value in hex, written at a very bad angle.
How is the, you know how you padded the last one where 0, 1, 0, 0?
Yep.
Isn't that 4?
So this would be, so we're still reading right to left. So this is still 1, 2, oh yeah, you're right, 4. Oops. Yep. I miswrote it then. Yeah, right? Yeah. Okay, my bad. Good catch. So a lot faster than converting that entire thing to decimal. Because if we converted the entire thing to decimal, you'd have to, first of all, know how many digits were in here, which I didn't even count. There's probably something like, what, 20 or so. You might even overflow your calculator if you're lucky and start getting floating point errors. So that's all sorts of bad. So if we go on to the next one, our next problem, we have base 8 and base 2. So just like the last one, we can use the trick, and that's, in this case, 2 to the third is base 8. So which means that binary and octal, which is base 8, also get to share that same kind of trick where you can do that. So in this case, we know that every digit in this octal number is going to be equal to 3 binary digits. So if I write this out really fast, 1, 4, 3, 1, 5. So just kind of block that all off. So I have to convert all these into 3 binary digits. Obviously 0 or 1 is 0, 0, 1. This one would be 1, 0, 0, 0, 1, 1, 0, 1. Oops. 1, 0, 0, 1, 0, and then 1, 1, 1. So if I write each one of these digits as their binary equivalents, then I combine all these together in a little bit more readable fashion. And there's your answer. Once again, a lot faster than converting that giant string to decimal. So jumping down to the next one, do this as fast as possible. I purposely put this one in here to see if people would make the mistake of just looking at these numbers and saying it's binary. I put it in base 3. So what that means is that our first digit here is worth, let's see how I can do this without running out of room. 3, and then, 1, and then 3, 9, 27. Let me just write all the numbers. Forget it. 3, 9, 27, 81, 243. Oh god, I wrote all these down somewhere. This is like what, 720, 729? Double check that before I write it. Yeah, 729, and then the last one is 2187. I'm going to move this up a little bit. So if I write all these and I put the bits just up this way, I shouldn't say bits because they're not bits in this case, but so we know that each of these values can be multiplied by their equivalent in the base. So if I multiply these over, I'll start at the bottom, we'll have 2187 plus 81 plus 27 plus 9 plus 1. So 3781 is 118. 118 plus that is, let's see, 2308, or 2305, excuse me. And that's in base 10. Okay, so that one was pretty easy. So now, I also, once again, wouldn't expect the numbers to go this high to 2187. I don't think you'll be expected to be able to do that on your paper. It's kind of a waste of time in that case. So the next one. So we have base 2 to base 6. We know that 2 to any power is not 6, so we can't use our trick here. So we will have to convert to decimal first, unless you want to do some fancy multiplication, which is just pretty much the same speed. So in this case, did I write it the right way? Yeah. So I have, this is 1, 2, 4, 8, 16, 32. So this is 32 plus 8 plus 4 plus 1. So 13 plus that is 45. And then we have to convert that to base 6. So 45 divided by 6 is 7.5. So 7 remainder 3. Divide 7 by 6 and we'll have 1 remainder 1. Divide that by that and we'll have 1 remainder. So now we have our column here, and we'll put those all out, and we'll have 1, 1, 3, and that's in base 6. So the next two we have down here also allow you to do the trick with the base. So we know that 3 squared is 9, which means that for every 2 digits in base 3, we'll have 1 digit in base 9. So I'll kind of break these up again. Yep, and I'll pad it with a 0 at the front just in case. So in this case, we know the first one is going to be worth, have a weight of 1, and the second digit will have a weight of 3. So we'll have 3, and then 2 plus 6 is 8, 3, 1, and 2. And then that should be our final in that case. So this is kind of why I made sure to put these on here, is to make sure that you guys are comfortable doing this, because if you get questions like this on your exam, it will save you so much time compared to taking this all out to whatever power and having to kind of splay out all the values and doing this method we did up here with, if you were given 20 digits, it's going to take you like 5 to 10 minutes to solve that. So our last one is once again the same type of idea. We have base 4 to 16. So 4 squared is 16. So we can say groupings of 2. So first one worth 4, the second one worth 16. Or sorry, 1 and 4. Gosh. So 1 plus 12 is 13. Our 1 plus our 8 is going to be 9. 3 plus 8 is 11. So that was the third pad over. Let me scoot these all in a little bit, just so I have room. So then we have 4 and 1, and that's 5. We have 3 and 8, and that's 11 again. 2 and 1 is 8 and 1, and that's 9. 1 and 1 is 4 and 1, and that's 5.
How are you getting 2 and 1 is 9?
Did I make a mistake?
No,
So since it's base 4 and we're doing pairs, the first one is going to have, so let's see, where is it? 2, 1. So the first one's going to have a weight 4, and the second, I'm saying 4, up to 4 of 1, and the second one's going to have a weight of 4. Just like in binary, the first one has a weight of 1, and the second one have a weight of 2, and et cetera, et cetera. This one's going to be worth 1, and it's going to be 2, and the second one's going to be worth, that was supposed to be 2 in this case. It's going to be worth 4, and that'll be 8 plus 1, and it'll be 9. So that was that one, 11. Then our last one is 4 times 3 is 12, plus our other 2 is 14. So now that I've converted those to kind of the decimal representations of each digit, we'll just make the digits really fast. So 13 is going to be D. 9, and then 10 is A, so we know that 11 is B. 5, B, 9, 5, and then E. And that'll be our final value, base 16. So, like I said, just watch out for powers of each other. It'll save you a lot of time. Especially Dr. S, I can totally see him basically using this to kind of exploit the amount of time you're going to waste on a problem. So, is there any questions with this before I move on? It's pretty straightforward. Okay. What's my time looking like? 45 minutes? Okay. So, bitwise operators. So really quickly, we know we will be dealing with basically AND, OR, XOR, inverting it, and then left shift, right shift. Sorry. So just kind of all the ones we have. So like AND, OR, XOR, invert, left shift, right shift. Really all that we can ever have in these. So first step in all of these is going to have to be, we're going to have to convert to binary. If you want to be fancy and put it in hex and do it in hex, that is possible, but I probably wouldn't recommend it. I expect all of you to put it in binary. So I'm going to save us the time of switching all these over and redoing kind of the work we've already done. So 34 in binary is 1, 0, 0, 0, 1, 0. And then 42 is going to be our 1, 0, 1, 0, 1, 0. So just like in our normal operations in all programming languages, we're going to work our parentheses then outwards. So we'll solve our parentheses first. We're going to do our 34 ANDed with 42. That is an AND symbol and not an 8. So if we do our AND on this, it's only going to be true when it's 1 and 1. So we'll go across and we'll do each of those. And then we know that we have to take that result and we have to XOR it by 11. So 11 in binary, I'll just put dot, is going to be 0, 0, 1, 0. I've padded it with zeros just so that everything lines up, because these extra bits will matter depending on your operation. And then 1, 0. And then I'll XOR that. So if I XOR this, we know that it has to be a 1 and a 0 for it to be true, and if it's 1, 1, or 0, 0, it'll be false. So we'll have 1, 0, 0, 1, 0, and then 1. And that'll be our final answer in this. And we could convert it to decimal if we want, but I feel like we have done enough of that to not. And I'll just put a base 2 symbol there. So pretty straightforward. Just remember to do your operations in the same order. I would never expect any of the professors to give you guys like multiple symbols in the same line and for you guys to figure out the order of operations of all these symbols. I know Dr. S wouldn't personally do that to you guys, and I don't think McAlpin would, or Hughes. I doubt you'll be expected to remember the order of operations of each of these operators. So our next one is 22 or 51 ANDed with 25. So just like I said before, we're going to work from our parentheses outwards. So 22 and then 51. So 22 is 0, 1, 0, 1, 1, 0. And 51 is 1, 1, 0, 0, 1, 1. And we'll, oh god, I don't want to write the OR symbol here because it'll look like a 1, and I can only imagine the repercussions of that. So if I OR it, anything that's where there's a 1, we're going to have a 1. So 1, 1, 1, 0, 1, 1. And then we'll take that result and we'll AND it with 25. So 25 in binary is 0, 1, 1, 0, 0, 1. And then if we pull this guy up, we'll have 1, 1, 0, 1, 1, 1. Then we're ANDing that. So if we AND it just like before, we'll do 1, 0, 0, 0, 1, 0. And that will be our final answer in base 2.
Would they want it in like decimal, or would they want it in binary?
They might, it would depend on the question. I could see them going either way. I mean, like I said, if we're asked to convert this to decimal, I think we've covered that enough at this point with that last page to know how to do it. It's not like they're going to hammer you with like 3 pages, or 2 pages of this like I am. It would likely be like a couple questions that would involve like all these things into one. They'd be all like overlapping into one question. Especially the last one. The last one here isn't pretty. So 19, 23. Like I said before, we'll do our parentheses outwards. 19 is 1, 0, 0, 1, 1, 1, 0, 1, 1, 1. Yeah, I wrote that right. And then we're XORing it. So 0, 0, 1, 0, 0. That's not bad. And then we're shifting it to the left by 2. So if we're taking this entire thing and shifting it over, we're going to have 0, 0, 1, 0, 0, and then our 2 extra digits that we're shifting in. So we're padding from the right with our zeros. And then at that point, you can drop your 2 zeros, and that's just 1, 0, 0, 0, base 2. Which in that case is like what? 1, 2, 4, 8, 16? Yeah. So that's pretty straightforward still. Your shifts, just remember that you'll always enter pad with zeros in this setting, in this class. I don't imagine they're never going to ask you guys to pad with anything different, so just always push in zeros from either side. Another important thing to remember really fast, actually. So this value. If we look at this value, right, this is 1, 2, 4, so that's 4 in this case. This is 16. So we shifted it by 2. So this, in other words, when we shift by 2 to the left, right, we're shifting each bit over, which is the same as multiplying all of these by 2. So if we took this operation, we multiplied it by 2, right? So if we took 4 and we multiplied it by 2, we're going to get an 8, which is just a 1 right in this position. So every time we bitwise shift left, it's the equivalent of multiplying by 2, and every time we bitwise shift right, it's the same as dividing by 2. And that's kind of the premise of integer division and so on. It's important to remember, though, that you can only ever do this with powers of 2. So if you want to divide by 4 or 16 or 32 or something, you can do it with bitwise shifting. But don't try to do it if you're dividing by some other value. So in this case, we shifted by 2, so we're multiplying it by 2 to the 2, which is 4. 4 times 4 is 16. So moving on to our last part here. So we have 15 left shifted by 3, ORed with 23, and then we invert it. We're going to assume this is 32-bit integer. This would technically depend on a few things, but we're just going to make that assumption. So if we take 15 and we represent it, we know that that's going to be basically 16, but minus the 1, so it's going to be all 1s. So we're going to take our 15 here, and we're going to shift it left by 3, which is going to be the equivalent of multiplying it by 2 to the third in this case, which is our 8. So 8 times 15 is like what? 120 or something. So if we slide all those over, we're just going to basically 1, 2, 3, 4, and then 0, 0, 0. So now we'll have to do our OR by 23. So then 23 here. Is on the paper? Yeah. So 23 in this case is, let's see, 1, 1, 1, 0, 1. And then we're doing I'm just going to write OR. So when we do that OR, these zeros don't really matter in this case, but I'll draw them nonetheless. So 1, 1, 1, 1, 1, 1, 1. Pretty straightforward. So we have this string of 8 ones now, and we have to invert it. So when we're talking about 32-bit integers, this isn't very pretty. So I'm going to kind of shorten it. So we know if we invert it, every invisible 0 that we're not looking at right now in front of this, up to our 32 bits, is going to flip to a 1. And we know that these are going to flip to zeros. So at the end here, we're going to have 8 zeros, 6, 7, 8, and then we're going to have 24 ones, because it's a 32-bit integer. So if we have 8 ones, then we're going to, or 8 zeros, then we're going to have 24 ones trailing it from the inversion. So rather than write all this, I'm just going to like put trailing dots and label this as 24. So now, if we wanted to actually get this in decimal, this is obviously a little bit uglier. So we're going to have to do the addition by the negative int max, which I personally don't have that value memorized off the top of my head, so I'm not going to like kind of show it. But if that was ever given to you, you would be given that value. You don't have to have it memorized or anything. So the important thing to kind of remember that, and that I'm going to mention this really quickly, is that the reason why you guys have that ugly method of where when you do that inversion, you add these values to the negative int max and yada yada, is that when we look at our negative maximum integer, or maximum like negative integer, it's not the same value as our positive maximum integer, because one of our positive integer slots is taken up by the 0. And rather, when they were making binary way back whenever, and deciding all this, it was decided that rather than wasting an extra bit every time on having a positive and a negative 0, that they would just leave it as that 1, 0 and have a negative int max. or a negative max that's like of magnitude 1 greater than our positive. So probably all thinking, why do we care, right? And that's because there are cases that you'll see that you can get in code, and it'll make you really mad when you find it, that you'll have a positive maximum integer or a negative maximum integer, and you'll invert. If you invert the negative, you're not going to get the same opposite value you're expecting. You're not going to get negative. You can't represent that in an integer, right? If you say -1 times int min, this will crash your program if you're storing it in an integer. This is not equal to int max. They're different, and it will cause, somewhere down the road, this will cause an issue with one of your programs, and it will make you mad. So, am I good to move on? Oh.
So there's 7 ones right there on the left answer, but on the right we have 8 zeros. Where's the 8th zero come from?
Did I have 7 there? Miscount? Wait, did I on?
The bottom right answer is 8.
Did I?
Right.
This should be, oh yeah, you're right. There's 1 extra. Sorry, this should be 25. Good catch. There should be 25 ones and 7 zeros. Good catch.
For a negative number, wouldn't you want to, like if you 128, isn't the, like if you not it, isn't it just negative like 128 minus 1?
So yes, you can also, yeah,
Okay.
this will work out. Yeah, everyone else is saving that. Yeah.
Does it matter if we're using 2's complement or any of that stuff?
So this all accounts for 2's complement. So when we do this knotting, that's why 2's complement exists, is to cancel out that -0. So the key way to think about it, right, is that, like he just said, if we're taking our, we have like a negative integer, like the maximum size negative integer. So, and when we're talking about negatives, it's really just the 1 trailed by a bunch of zeros. When we invert that, we're getting the maximum size integer, right? So we're going from these kind of back and forth of kind of 2 very different numbers. When we invert if we have like 0 and we invert our 0, we're not going to get like 0 like we'd expect. We're going to get -1, which is kind of where that whole offset comes from, which is why 2's complement exists. Which is why when you do 2's complement, you invert all your bits and then you add 1. It's to kind of account for that whole memory discrepancy they wanted to do to keep everything efficient, which in the long run matters, right? I mean, if we have variables here and every single variable took up 1 more or had 1 less value than necessary, there's a lot of systems where that could matter. Okay, so any other questions? Okay. So these are kind of all theoretical questions, and I'm going to try to talk about these as much as I can because we don't really have time in this setting to do backtracking problems and write out all the code. So first question on here was just what are the basic components of a backtracking algorithm? I just want to put like a star next to this and say this is very important. I would almost guarantee that one of your coding questions, if you have one on your exam, will probably be a backtracking problem or filling in part of a backtracking problem, whether it's writing a base case or filling in a line or saying what condition you, what new values you're generating. So there will be some question in backtracking. It's pretty much guaranteed. And if you don't get one in your final, you would get one on the foundation exam. So our basic components. So we know that since backtracking is always going to be using recursion, we're going to have base cases. We have to have some condition to break out of our endless recursion. So I'm going to put base cases. And then our next step is usually, I'm going to put the optional flag here, is depending on how exactly your algorithm is sometimes we have to check for our duplicate states, right? This isn't necessary for every problem, but for some there are, and I'm going to discuss the differences in a minute. And it's basically saying, okay, well, if we go through this puzzle and we end up in the spot we've already been in, we obviously don't want to keep backtracking from that location because we'll just end up in an infinite loop of recursion, and that's obviously going to crash. So then our last kind of big step is generating our new moves or solutions. So this is where we want to generate what cases we're going to recursively call into. And then inside of that kind of premise, we have to make sure that they're valid. we have to make sure, we have to change our state. So we have to make sure that every state we go to is valid, and this can kind of be done in multiple ways. Sometimes we'll implement this when we're generating our recursive calls, and sometimes we'll check this as a base case. So we'll say like, okay, is our puzzle we're at still valid? Is our guy standing in a wall in a maze he's in? Is he, are we doing a Sudoku algorithm and we're inserting a value that we can't insert anymore? There's always some limiter on whether we're in a valid state or not. So then we have to do our recursive call basically. So this is going to be where we're going to change our state and then we're going to do recursion. So calling into that next state that we're going to be in. And it's important to remember that when we do recursion, even if we're making 9 states or 8 states for inside of each call, it's important to remember that we're making one of those calls and then eventually coming back up, right? So if I have like a tree where we're making like two or three different cases, and then we're going down to a node, this isn't going to make all 3 of these and then go to them. It's going to make this one, which is going to make its next one, and these ones are all going to have more. And it's just going to keep going basically what we call depth first. It's going to go through as deep as it can in this algorithm before it comes back up. So we call this depth first. You don't need to know that term, but I'm just kind of throwing it out there for when you guys take CS2. So this is important in some cases, but not all, right? So I'll kind of give a little bit more of examples of this in a minute, but let's continue. So our last 2 conditions here is that another optional one kind of, and that's that we're processing our return value. And the reason why I say this is optional is it's only if we have one. So not every backtracking algorithm has to have a return value. For example, if you're printing out a tree or you're printing out a try, it's still technically backtracking, but you're not processing any returns because you're just printing it out. So and that's basically this is determined by whether you have a void function or if you have a return value on it. And then your last one is just to like undo your backtrack / undo your state change. And when you look at all these steps, right, this looks like a lot. Like, when you look at all these steps we have to do for each of these, this seems kind of intimidating that we have to do kind of all these things inside of this function. But what I always say is that backtracking really isn't scary. It's really just recursion, and you guys have been doing it way longer than you think you have. Anytime you guys made something that went through a tree or went through a try, it was always backtracking. So we always went down in our try, and if let's say we were printing out our values or we were looking for a frequency, we always had to go all the way through and then somehow come back up and then kind of go down the other branches and go down another branch and go down another branch. And that was backtracking. And all we really have to do is a lot of these states will be combined into the same parts, and we just really have to make sure that we have a way back up and that we can make sure we can accomplish whatever goal it is we're doing. So this question I left kind of really open-ended for the next one is that let's say we were solving a Sudoku puzzle with backtracking. This is a really common basic backtracking problem. I know Guha did it for his CS2 program. Their first program of the semester was this. And it's a really common one to do, and it's a really good kind of practice one. So the idea is, hopefully we all know Sudoku, because I don't really have that much time to explain it, but we have a puzzle, and it's divided up into thirds, and then each of those thirds is divided up into thirds. And the idea is that if we're given a puzzle that has like a few of the little spots filled in, is that we can try every number in the first position, and we can try every number in the second position. We can kind of just try, okay, is 1, 1, 1, 1, 1, 1, 1 going to work? Or are we going to have issues? So in this case, we're going to, if we draw the tree diagram, which by the way, this is kind of important right up here, is that to remember that even though this backtracking for this problem wouldn't involve a tree or any sort of like a tree like that, there's a tree in the fact of like how we make our backtracking decisions. Every time I use a value, so let's say I try putting 1 in the first state. There's 9 values I could try off of that 1 in the next spot. And there's 9 values for each of those that I could try in the following spot. So it's still a tree. It's the shape of your options in your algorithm is a tree. It's just more of a logistic tree than it is a physical tree. So I said, what base cases might we check for in this backtracking algorithm? And while I know this seems really broad and seems like, oh, we don't see the code. How we know what base case to check for? we know that all these things we say up here, right? We know to check for if we have a valid state. So in Sudoku, a valid state would be, okay, I don't have a 1 in the same row as me if I'm a 1, and I don't have a 1 in the same column as me if I'm a 1, and there's not a 1 in my box already. So those, like for this case, like checking if valid, so like if we're checking if it was valid, it'd be like making sure same value isn't in our box or in our row. Oops, I spelled. And then base cases. If we're talking about base cases, and obviously we want to check make sure our state is valid, right? We don't want to keep backtracking and making recursive calls if they're already invalid, right? We want to make sure that every time we're making a case, that case is valid before we make any more. Because, well, a lot of these problems you guys have looked at is only like, okay, with a try, if we screw something up, we look at a couple try nodes twice, right? Like, who cares? In this one, let's think about how many cases this is. If we have an empty Sudoku puzzle, for this first case, there's 9 possibilities, and there's 9 possibilities for the next one, and there's 9 for that one. And there's a total of 81 squares in this. That means that if you tried every single value in every single position, that's 9 to the 81th power of recursive calls. That's a lot. Like, that's beyond a lot. So the idea is we want to throw out like 90% of those because you'll already have like a 1 here and you don't want to put another 1 there. We don't want to put, like, if there's a 3 right here, we don't want to put a 3 in any of these positions. So we should throw out more than like 99% of those before we even think about, like, even before we get to here. Another big thing is when we start this recursive call, right, we want to check to make sure everything's valid before we start. If they gave you a puzzle where there was 2 3s right here, you don't want to solve all the way through all these combinations thousands and thousands and thousands of times just to realize that, oh, they gave me a bad puzzle from the start, right? It's worth going through here and checking everything once beforehand. And then along with that, when we go through this puzzle, one of our base cases, the most obvious one, have we solved our puzzle? If we get to this last position and we put a value in it, it's either solved or it's wrong. It's an invalid position. So you want to make sure you're checking if your puzzle is solved. I've watched people make backtracking problems where they didn't check if their value was solved, and they just had infinite recursion, not because their algorithm was wrong, but just because they didn't check if it was done. So while all these seem like there's all these different steps, most of them will be included in the same gist of your programs. And just like all of recursion, these programs will be these functions will be really short but kind of thought intensive. So let's see, what other parts of this do we have? So we talked about checking our duplicate states. If I have this Sudoku puzzle, is it possible for me to generate a duplicate state? Okay, I see a couple people shaking their head no. Oh. No, you can't. So we can't, because if I put 1 in the first position and I put 1 here, when I backtrack, I'm not going to put 1 there again and put 1. These are going to be in for loops or something so that they increment to the next value. So it's going to try 1 and 1, 1 and 2, 1 and 3, 1 and 4, etc. And then backtrack and do 2 and 1, 2 and 3, or 2 and 2 and 2 and 3. So it's impossible for this one to generate a duplicate state. So there's no reason for me to ever check if I'm doing a duplicate state, and there's no reason for me to ever store one. Because checking for a duplicate state is easy to do. It takes up a ton of memory, especially in something like this. I'd have to store every possible puzzle solution, and we've already said there's 9 to the 81 of those. So trust me, we don't want to ever look at it. So I kind of also just covered the last part, so I'll write that in really fast. So in what situation don't we have to check for the duplicate states? When it's impossible for us to generate them. So there's plenty of backtracking problems you guys will run into later on that will be impossible to make duplicate states. For example, if we're doing something where we're always incrementing, we're always iterating forward, we can only really do it if we can go forward and backwards. And in this case, like the one I had, we will never go backwards, so we can't really ever make those old states we had. Is there anything else I want to say on this? And then for base cases, obviously make sure stuff isn't null pointers, etc. Make sure the data you've been given is valid. Make sure they didn't give you an array that's of size 5 when you need one of size 81. The simple stuff like that we're always going to be checking for. If you guys get a coding problem on one of your exams, because obviously for all of you guys know this already, I'm a TA for Dr. Zemansky. When we grade your guys' test, it makes me so sad inside when I see people that just leave coding problems blank. Like, put an if something is null, return 0, or return something. Like, your base cases take one line in 10 seconds, right? But they're going to be worth points. And it's like, there's people who will spend 20 minutes filling out this entire sheet of paper with some code that doesn't work right, and we have to give them 0 points. And then there's this person that spent probably 5 seconds on it at the beginning of the test and wrote something, the base case, and just got more points than that person that spent 10 minutes on it. Always put something down. It's just like when you guys are doing math problems or something, just partial credit. Put down the stuff that happens in every problem, and if you don't have the time to solve it, at least you'll have that. You'll have that couple of points that you got for free for putting the basic stuff that you always have to do. Those steps that we always follow. Even if you just put down like the steps and just put like, oh, for checking if valid, I'll check if this happens. Even if you don't have time to like actually solve it and write it in code, at least you'll have something there. Is there any questions or comments before I move on to the next part? I think that's the end of like the current material. I think after this, it's mostly reviewing old stuff with a little bit more in-depth analysis into it. Anything? Okay. So quickly, I'm going to try to do this part as fast as possible since it's not very exciting. So going through like some old sorts really fast, and basically I'm going to kind of rush through this part. So when we do quick sort, we know that our 10 is going to be our pivot point, and we know that we're going to have our right and our left that are going to move inwards. So when we do our right and our left, they're going to move until they have an issue. The left has one that's bigger than our 10, and our right is going to have one that's less than our 10. So in this case, they're going to immediately have issues, and they're going to swap. And then when we move them into here, we're going to perform another swap. And we're only doing one pass, so I can just fill these in immediately. Once again, we won't have an issue on that side, so we'll keep that one moving in, but this guy has already found his issue. So left is going to keep moving until this one, and those two are going to swap. And then at this point, they're going to cross, so we're going to end up swapping our last value to this position. Or sorry, to the 20. My bad. Oh, no, this other one. Yeah. So our 8 would have been swapped over to here, and then our 8 is our point where they crossed. So when we can do that, we're going to switch our 8 and our pivot, and we're going to get 10, 8, 9, and 2. Radix sort, I'll just start this one and I'll move on. We'll sort by the first number, so 152, 110, 440, or sorry, no, 440. The 204, 441, etc. So just sorting by the first index. And then in this one, this is the type of question you'd probably actually see for a sorting question. And that's that look at this array and look at after one pass of a sorting algorithm is passed, and determining which one is passed. So immediately look for the easiest ones, right? Look for if one value has been swapped, which would indicate something like an insertion sort or a selection sort, something where we're only moving like one value at a time. And then look for stuff that's really like radix sort. Radix sort is really obvious to spot, right? Because everything's going to be sorted by that first number and nothing else. And this one is a little bit trickier, right? But we see that our last value is now our highest one. So we have to think to ourselves, okay, what sorts move our biggest value to the back? And in this case, if we look at the way that everything's been affected, we can say, okay, well, it did all these weird swaps along the way. So this is bubble sort, because it did all these weird swaps, and it somehow moved our largest value to the back. So then at that point, we know it's bubble sort. These last two are pretty quick. So worst case runtime for quick sort. So if you've been to one of my sessions when we were talking about sorts, you've heard this. I think it's hilarious, and I remember I got points on the exam for this because I was making jokes to my friend about how stupid this was. And that's that if you give a quick sort a sorted array, exactly, it always gives it the worst case runtime. And I always think this is really silly, because then at that point your bubble sort, which is an awful sort, gets a better runtime than quick sort. And people that are set on using quick sort and not using a different one actually will randomize their array before they try to sort it, which is extremely counterintuitive. But the idea is that the chance that it's been given to you sorted is higher than the chance that will randomly be made sorted. Other ones for this is if it's opposite order, so 6, 5, 4, 3, 2, 1. There's a couple other little fringe cases like that, but basically making sure that we have to do the maximum amount of swaps and that we have to do every single comparison along the way. So this last one is something that's kind of combining new material with old material. I said which one of these sorts has the best worst case space complexity. So which one takes up the least amount of space in the like the worst case scenario. So you said, what did you say? Yeah. So in this case, it's selection actually, which is the opposite of your normal runtime, right? When we talk about normal runtime and time complexity, selection sort is obviously the worst one out of all of these, right? Like these are all either n log n sorts, or they're better than that. But all of these take up memory, right? Counting sort, we have to have a frequency array. For merge sort, we have to have our recursive calls. And then for radix sort, we have to have our buckets. So all these use up memory that we might not have or whatever. Well, selection sort just does swaps. So while it's the slowest, it also takes up no space, which is obviously can be an advantage. So my last page is just linked list reviews. So I think I'm going to pass on that, and I'll post the solutions for this on our website probably tomorrow, because it's 10:30, to be quite honest. So before everybody flees out of the room, I'm going to quickly ask that you guys just fill out this sheet of paper. It's just evaluations for me and for Sark. So I'm going to pass these out really fast. These are one sheet front. It will only take a minute. And then I'm going to collect these. There's some for you guys.